Tonight, we drift into the thinking dark, the quiet between stars where questions keep small fires. The room settles, breath finds a tide, attention loosens like a sail in evening wind. Out there, patterns we trust merge with patterns we only feel by touch, as if the universe were a door we lean against, warm, closed, and patient. Some mysteries shine, others are the sea they float upon. We watch galaxies curve around an unseen scaffold. We measure a soft pressure in emptiness that coaxes distance to grow. We catch radio flashes that last less than a heartbeat. We see two island galaxies sliding toward a meeting they cannot avoid, even as the fabric around them slowly stretches. We read riverbeds on Mars and look for the water that vanished. We hold moon rock and hear the memory of a sky turned briefly to glass. These are not fractures in knowledge, they are places where knowing breathes. Two careful clocks disagree about how fast space expands. Whole clusters drift toward a hidden basin. Quiet particles slip through us by the trillions. Each seam is a promise that something real waits just beyond our present words. Even life's first steps seem written in starlight. In the cold of interstellar clouds, simple molecules learn their choreography on grains of ice. Comets carry those lessons to warm shores. In the lab, strands and vesicles stir. They do not yet wake. The missing piece is not a spark, but a rhythm that remembers itself while it changes. Some edges are mirrors. A white hole appears in the mathematics when time is reversed. In nature's weather, it fades. The universe has no rim, only horizons that move as time moves. We cannot reach them, yet they shape all we can see. The great attractor is not a throne, but the lay of gravity's land, a low place that gathers many small streams into one wide current. None of this asks for urgency. These are invitations, not alarms. The cosmos is not broken. It is larger than our first language for it. Imagine a library at night. Some books shelved, some open, some still being written in a hand the eye will learn to read. Before we begin, let us gather our little midnight crew. If these voyages bring you ease, a gentle like or a simple subscription helps this calm reach others still awake. Tell me the hour you're drifting tonight in the comments, whether that may be midnight, 2 a.m, or even dawn's edge, so I can chart our resting constellation and time future journeys to meet your night. And if you want to sink deeper, the Midnight Voyager playlist is waiting. Now, allow yourself to settle. Let the breath fall in and out, unforced. We are going mystery by mystery now, one clear facet at a time, letting each cool the mind and widen the room. When you are ready, we begin a quiet voyage through unsolved cosmic mysteries, questions that feel impossible and somehow make rest easier to find. The outline of the moon's origin looks clear from a distance, a colossal impact in the early solar system, Earth and an intruder briefly becoming one incandescent body, a ring of debris that gathered into our companion. Step closer, and the drawing fills with unanswered lines. The mystery is not whether a great collision happened, it's how that single idea can satisfy the many, precise questions the moon still asks. What was the impactor really? We give it a name, Theia, and then almost everything about it goes soft. Did Theia form near Earth and share our chemical accent, or wander in from farther out with a different mix of elements? Was the strike a glancing blow, or nearly head-on? Was the speed ordinary for that crowded era, or unusually high? Each choice shifts what should be left in orbit, what should fall back, and what should be lost to space. And none of the choices yet fits every clue at once. Chief among the clues is sameness, where difference is expected. Moon rocks and Earth rocks carry nearly indistinguishable isotopic signatures in oxygen, titanium, tungsten, and more. If the moon were mostly Theia, and if Theia were a typical neighbour, the isotopes should lean apart. They do not. Did the collision mix vaporized rocks so thoroughly that Earth and Theia became, for a moment, one blended body before separating? Did the system balloon into a hot, donut-shaped synestia that erased all regional accents before the moon condensed from the shared cloud? Or is the likeness telling us Theia was born in Earth's very neighbourhood, matching our composition from the beginning? 3 possibilities. 1 sky. The moon keeps its counsel. Even the moon's dryness is not the quiet verdict it once seemed. A world forged in fire should have bled off its water, yet tiny glass beads from ancient eruptions hold traces of it, and mantle samples hint at more. How did volatile elements survive a boil-hot birth? Were they sheltered in deep pockets and released later through volcanic breaths? Did comets and hydrated asteroids resupply the surface in careful measure? The numbers are small, the implications large. The answer touches not just the moon's story, but the rules of what can live through cataclysm. The near side and the far side speak in different voices, and we do not yet translate them cleanly. The far side's crust is thicker, the near side is thinner and stained by vast dark seas of basalt. Did the newborn moon lock quickly, with one face toward Earth, basking in steady earthshine that kept the near hemisphere warmer and slower to crust? Did the moon accrete asymmetrically from a waning disk, piling more material on one side than the other? Did early tides stir heat in patterns that froze the crust unevenly? Each mechanism can draw part of the map. None traces every contour of the dichotomy without lifting the pen. Orbit adds its own riddles. The first path must have circled just beyond the Roche limit, alarmingly close to Earth, tides like moving mountains. From there, the moon drifted outward, and it still does. That part is steady. What remains open is the choreography. How fast did recession proceed in the beginning? Did the orbit pass through resonances, like the evection with the Sun, that pumped the eccentricity or tilt, which values of Earth's tidal cue, its internal dissipation, were true then? And how did they change as oceans and crust evolved? The present inclination of the moon's orbit is awkward to achieve in simple models. Damping and excitation fight, and the numbers do not yet agree without special pleading. Time is another soft edge. Did the moon assemble in a single catastrophic event, or as the last sum of several smaller collisions that each threw up a short-lived ring? Multiple impact models can help with isotopes. Single impact models fit angular momentum more cleanly. The high-energy hit-and-run scenario can make the math smile, then frown again when volatiles and mixing enter. The dates we read from crystals and basalts, ages of crust, basins and lavas, pin milestones, but they do not yet string themselves into one unbroken sentence. Inside a small core and a long-lived dynamo leave another open door. Magnetic signatures in Apollo samples tell us the moon once had a global magnetic field, strong and persistent for hundreds of millions of years after formation. What engine powered it? Was it a convecting, sulfur-rich core that crystallized slowly and stirred its own metal? Or was it motion from outside, precession of the whole moon under Earth's pull, shaking the core into activity? Or were large impacts episodic jump-starts rather than a steady battery? Each option carries a different thermal history and interior structure. None has yet claimed the field beyond doubt. The chemical oddities gathered in the Procellarum creep terrain, the near-side's enrichment in potassium, rare earth elements, and phosphorus pose another question. Is that province the residue of the last incompatible drops crystallizing from a global magma ocean? Is it the chemical shadow of a colossal early basin, or the mark of asymmetric heating that changed which melts could rise? Depending on the answer, the moon's early heat budget changes, and with it the tempo of volcanism that painted the near side dark. Even Earth's tilt may carry a memory we cannot read cleanly. Did the impact that made the moon also set Earth's obliquity and stabilize it thereafter? Did it strip an early atmosphere or merely bruise it? How much angular momentum was traded between spin and orbit before tides settled the partnership we live with now? The subtleties matter: climate stability, day length and tidal rhythms, all the quiet metronomes of habitability, lean on the details of that exchange. If there was a Theia, where is it now? Some models leave most of its iron in Earth's metal core, and much of its rock mixed into Earth's mantle. Others let a Theia-rich fraction seed the Moon's interior. Geochemical hints, tungsten isotopes that remember ancient metal-silicate separation, have been read both ways as measurements refine. Perhaps Theia's signature is everywhere and nowhere, blended past recovery. Or perhaps a faint specific trace waits in an as-yet unsampled depth, a page we have not turned. What would count as progress that feels like closure? A model that reproduces, in one continuous calculation, the observed isotopic near identity, the right angular momentum, the volatile inventory, the near far side asymmetry, and the present orbit, including inclination, without invoking special, delicate initial conditions. A seismology network on the Moon's far side to detail the thickness and layering of the crust. Samples from the South Pole Aitken Basin and the far side highlands to extend the timeline and the chemistry beyond Apollo's reach. Tighter ages for the first crust and the last lavas. A magnetic record that fixes the dynamo's birth and fade. Each of these exists as a plan, none yet as a finished page. Until then, the Moon holds its mystery the way a well-made bowl holds water. Quietly, with a shape that invites use without giving up the potter's secret. We know the broad curve, an impact, a ring, a gathering, a long outward drift. Inside that curve, the unsolved portion keeps its exactness. Which impact, which mixing, which path through heat and tide? Why this face and not some other? Those are the questions that keep the Moon from becoming ordinary and keep our nights a little more awake than they would otherwise be. The map looks certain. Valleys that branch like river systems, deltas built grain by grain, shorelines sketched around ancient basins. Mars wore water on its face. What we do not know is where that water is now, and how the planet moved from running blue to breathing dust. The mystery is not one gap, but several, braided together. Begin with the thinnest clue that is also the strongest: the air. Today's Martian atmosphere is too fragile to keep liquid water at the surface for long, yet stones remember lakes. So either the air was once much thicker, or warmth arrived in pulses that let water flow between long freezes. Which story is true? A sustained temperate Mars would leave blankets of carbonates and other chemical archives. We see some, not enough. A punctuated Mars, brief warmings after big impacts or bursts of volcanism, fits the patchiness, but strains to explain the size and order of the old river networks. The climate could have switched between these modes. We do not yet know the cadence, next the fingerprint in hydrogen. Compared with Earth's oceans, Martian water today is enriched in heavy hydrogen, deuterium. That is what escape does. The lightest atoms leave first. The ratio says a great deal of water was lost to space, but it does not say how much remains below. How much oxygen, left behind when hydrogen fled, escaped with it? How much oxidized the crust? The planet's redness hints at one answer. Models of escape hint at another. The budget does not yet close cleanly. The shield is another hinge. Early Mars seems to have had a magnetic field. Later the dynamo died, and the solar wind could pull at the top of the sky. We can date the loss roughly. We cannot yet thread a timeline that tells whether rivers faded because the shield failed, or whether both were symptoms of deeper cooling. Did the dynamo's last years overlap the last big lakes? If they did, perhaps the end of magnetism tipped the balance. If they did not, the climate may have been changing for other reasons. Volcanic gases thinning, hydrogen trickling away, obliquity sliding the caps back and forth. Storage complicates the ledger. Some water is obviously parked. Polar ice caps, layered like pages, buried mid-latitude ice that radar can see. Crystal water in clays and salts. But how much hides in a rock pores kilometers down? How much sits as ancient ground ice under dust? How much can be released back to air under any plausible climate? The subsurface is loud in inference and quiet in proof. Reports of liquid brines beneath the South Polar layered deposits were thrilling. Later analyses allowed dry explanations, or slurries colder than any easy biology. The signal is ambiguous because the instrument is far and the physics of dirty ice is subtle. The question, does present-day Mars keep lakes in the dark, remains open without scandal. There is also the shoreline that will not settle. Some long level lines near the edges of the northern lowlands look like coasts. Other data argue they are tectonic or isostatic scars, or that a true ocean surface rose and fell as the planets spin and gravity redistributed the water and the crust responded. If an ocean existed, how deep? If it did not, why do deltas and outlet channels point toward a missing sea? Mapping improves, interpretations trade places. The ocean is a hypothesis that refuses to declare victory or defeat. Modern trickles were once a temptation. Dark streaks that lengthen on warm slopes and fade in the cold seem to speak of brines. Later, their timing and behaviour match dry flows, fine grains slipping down slope in thin air. Perhaps some brines exist as films in soil for minutes, perhaps they do not. This is not yet a contradiction. It is a reminder that the present is a different climate, and that today's water, if any, moves by rules that deny us riverbeds. Tilt, the planet's obliquity, moves the goalposts. Mars leans more wildly over long times than Earth, and when the angle swings, ice migrates. At some tilts, the poles warm and lose mass while mid-latitudes gain mantles of dust-laden frost. At others, caps thicken and deserts widen. We can read these cycles in layered polar deposits and smoothed icy mantles in the mid-latitudes. What we cannot yet do is convert those layers into a continuous water ledger. When exactly did major transfers happen? And how much liquid ever reached the surface during the warmest parts of those swings? Energy sources, how to keep water above freezing under a faint young sun, remain a core enigma. A thick carbon dioxide blanket alone struggles. Add hydrogen or methane from volcanism or serpentinizing rocks and the greenhouse strengthens. Add dust and clouds and the picture shifts again. Did early Mars run on a H2CO2 greenhouse for a while? Did impacts inject enough heat and vapour to make transient seas? Did frequent volcanism pulse the climate like a slow heartbeat? Each mechanism is plausible. The right mix and sequence are still guesses that change with every better model and every new mineral map. Escape to space can be watched now, but must be inferred for then. Today, the upper air loses oxygen and carbon in a steady thin outflow under the solar wind's touch. Scale that back to a younger sun, add sputtering and photochemical escape, fold in the on-again, off-again magnetism, and you can lose ocean's worth over eons. But ocean's worth is a soft number unless the sinks in the crust are counted. If the rocks did not swallow as much oxygen as required, more must have escaped. If they swallowed more, less needed to fly. The chemistry of the deep crust is a missing chapter. Even the rivers themselves raise questions. Some valleys look like systems carved by long-lived rainfall. Others resemble catastrophic outflow channels, fed by pressurized groundwater breaking free. Were there two hydrologic regimes, gentle and violent, alternating as climate and interior heat changed? If groundwater fed many channels, how was that water recharged without a persistent hydrologic cycle at the surface? If rain did the work, where are the long stacks of lake beds we would expect everywhere? We find some, not enough to quiet the debate. What would answer these questions without hand-waving? A dated core from a delta that pins a lake's lifespan, not just its presence. A borehole into mid-latitude ground ice that measures age and impurities layer by layer. A clean inventory of crustal oxidation, state at depth over broad regions. To close the oxygen budget. A tighter clock on when the dynamo died relative to the last stable waters. More complete maps beneath the zone of avoidance of Mars, the radar-opaque places where dust, topography, and composition hide ice in forms our current instruments only hint at. None of these is impossible. All of them are heavy lifts. For now, 3 broad answers compete politely. First, the lost to space picture. Much water dissociated and bled away once the shield failed. What remained froze or bound into minerals. Second, the buried world picture. Large fractions of the water retreated underground early and still sit as ice or deep brine in a cryosphere that only rarely vented to the surface. Third, the punctuated climate picture. Most visible carving happened during short, global thaws triggered by impacts or volcanism. Between them, the planet was cold and dry, moving water mostly as vapour and ice. The truth may be a braid of all 3, and the braid's thickness may have changed through time. If you want one image that keeps the questions honest, stand on a ridge above a fossil delta. The fan spreads into a basin that once held a lake. Pebbles on the ground are round from running water. The air is thin, the temperature shy of freezing, the sky a pale rust. Under your boots, ice may lie clean and blue a metre down. Miles deeper, rock pores may hold brine that never sees the light. Overhead, atoms still leave the planet, a slow thread towards the sun. The scene answers, was there water, and refuses, where is it now exactly, and in what proportion of sky, ice and stone? That refusal is the unsolved portion. It is not a wall, it is a map with pale corners that future drills, returns and long watches will darken in. On clear nights, there is a faint place in Cassiopeia's direction, where the dark feels slightly thicker, as if the sky were holding its breath. That dim smear is a galaxy like our own, seen from the side, and it is not staying where it is. Across a gulf that numbers cannot soften, Andromeda is coming toward us. Space itself is stretching, yet these 2 islands drift together. The paradox is gentle once you know the rule. On the grandest scales, the fabric grows. Galaxies ride apart the way points on a rising loaf separate. But within knots of gravity, the thread is already gathered. The local group, our Milky Way, Andromeda, Triangulum, and dozens of small companions, has tied itself into a small country in a widening world. Inside that country, gravity speaks louder than expansion. The sea swells, the boats still row. We can tell Andromeda is inbound because its light is shifted towards blue. Most distant galaxies redden as their light is stretched by expansion. This one does the opposite. Blue shift does not tell the whole tale though. A sideways drift could carry it past us with only a curt bow. Measuring that sideways motion is like noticing the hour hand while standing on a carousel. It took patient stares from space telescopes and star-by-star comparisons to learn that the sideways speed is small. The path is not a miss, it is a meeting. The meeting will be slow by any human sense, quick by cosmic habit. In billions of years rather than millions, the 2 spirals will draw near, pass through each other's disks, and then, after long arcs and soft breaking by tides, settle into a single, rounder city of stars. That future galaxy has a nickname already, Milkomeda. It is a practical name with a dreamy sound, a reminder that the ordinary and the mythic share a border. When galaxies pass, almost nothing solid strikes anything else. The emptiness between stars is generous. Collisions happen more often between clouds of gas, and between the great invisible halos of dark matter that surround the bright disks. Those halos reach out first, grip and raise tides. Gas flows feel the pull and the squeeze. Clouds compress. New stars light. The disks tear long rivers from one another. Tidal tails that arc into space, thin and elegant as script. Some of that script will fall back and write itself into loops. Some will thin into streams that wrap the remnant in lace. At the centres, 2 dark objects wait with the patience only gravity knows. Ours is a few million suns in mass. Andromeda's is many times heavier. As the galaxies merge, these black holes will find each other by listening to the slow noise of their own wakes. They will circle closer and closer, stirring stars like spoons through a shallow bowl. In the final approach, they will send ripples into space-time itself. Those ripples will leave without sound, like rings on a lake that no shore can see. From here in this era, we can only guess what the sky will look like to whatever eyes are watching then. At first approach, Andromeda will swell into a great oval, bright enough to cast a pale shadow. Lanes of dust will braid the Milky Way zone. After the first pass, the night will wear bridges of starlight. Later passes will bring knots, and knots will unspool. The poles of the old discs will tilt and wander. The idea of constellation will become a local story told to comfort children who do not remember other shapes. None of this will be abrupt. The future sky will change with the patience of lichens, of dunes, of glaciers. It will be a long, unhurried spectacle that no one mind can own from start to finish. Our star's fate is not a single thread, but a bundle of possibilities. The sun circles the galaxy now, like a small light on a wide carousel. During the first tides, its path could bend outward to a calmer suburb, or inward to a busier district. It might be pitched into a halo where nights are dark and spare. Direct collisions with other stars are unlikely. A close pass is possible, but rare. If planets around distant suns have watchers of their own, they will see our star slide by without a word. The drama is in the map, not in the knocks. Triangulum, the smaller spiral to one side, may join the dance or keep its distance depending on threads we still measure. It could become a companion to the forming remnant, or it could arrive later, like a guest who found a longer road. The details of this choreography matter to astronomers for what they reveal about dark matter halos, gas flows, and the way galaxies grow quiet after long youth. To a quiet listener before sleep, they are reminders that even the largest patterns have turns we have not learned to predict. The mystery here is not whether a merger will happen, but how it will write its long sentence. Computer models can be coaxed to show one future or another by small changes in starting conditions. A slightly different angle, a little more or less dark matter, a touch more gas, and the same story ends with different punctuation. The shapes of the tidal tails, the timing of starbursts, the final tilt of the remnant's rotation. These are questions with answers that depend on measurements we are still refining. It is not ignorance, it is weather we have not yet charted in all directions. There is a calm contradiction folded into this chapter that the mind seems to like. The universe expands, and yet some parts of it pull together. We live inside one of those parts. The expansion does not stop at the border of the local group. It rolls on beyond, carrying far galaxies away until their light grows thin and then thinner still. Here where mass has gathered, the sea runs outward while the harbour stays. Picture the local group as a cluster of lanterns in a slow current. The current moves, the lanterns drift apart, but the ones tied by cords do not leave each other's company. The cords are the halos, the dark matter, the common fall of gravity. In time, the tied lanterns will knot themselves into one brighter lamp. Beyond their glow, the current keeps the rest of the river sliding toward a horizon no boat can reach. If you want a single image to keep, choose a bridge of stars. It begins as a faint curve between two islands. It thickens as tides draw a river from one shore to the other. It thins as the river pours back in arches and loops. No creature ever walks that bridge. It is stone made of suns, a path that draws itself and then erases itself, leaving only streams and shells to show where it has been. Somewhere on that bridge, in that drawn and redrawn line, the history of our sky is written in letters too large to read, yet plain enough to feel. Begin with a confession that astronomy makes without shame. Most of the Milky Way is built on scaffolding we cannot see. Not a faint fog, not shadowed dust, something that does not shine or absorb, yet holds stars in their orbits as firmly as a hand holds a thread. The proof is quiet and cumulative. Out where a spiral's light thins, the stars should slow, the way planets slow with distance from the sun. They do not. The rotation stays stubbornly high, as if the disk were embedded in a deep, invisible halo. The equations that fit our inner neighbourhoods demand more mass in the dark beyond the lamps. Clusters of galaxies tell the same story with a different accent. Their member galaxies move too quickly to be bound by the light we count. The gas that fills the space between them is hot enough to glow in X-rays, yet even that bright mass comes up short. When such clusters pass through one another, the gas collides and lags. The galaxies, mostly empty space, glide on. Gravity, however, lies with neither, but with an unseen component that keeps going. Mass that neither shines nor stops, traced by how it bends the light of still more distant galaxies into arcs and smears. The lens reveals a weight that light ignores. Look farther back, and the afterglow of the young universe murmurs the same refrain. The tiny ripples in that ancient microwave light act like a fossilized sound, pressure waves in a plasma, frozen when the cosmos became transparent. Their pattern fits best when most matter is non-luminous. Change the mix and the music goes out of tune. Keep the dark and the peaks fall into place. From those ripples forward, simulations weave a web of filaments and knots, structures that resemble the observed large-scale sky, if, and only if, the strands are tugged by a dominant, invisible mass. We give the unknown a plain name: dark matter. The literalness is deliberate, the mystery is big enough without embroidery. If you want an image, think of wind known by grass. The grass does not invent the wind, it reveals it. In galaxies, the wind is gravity from an unseen halo. The grass is every orbit, every lensing arc, every gentle mismatch between what shines and what weighs. What could the dark be? One family of ideas imagines new particles, quiet, slow-moving masses that ignore light but feel gravity. They would be cold in the technical sense, not that their temperature is low, but that they drift rather than race, allowing structures to clump early and well. Some versions would occasionally jostle ordinary matter. Deep underground, detectors wait for such nudges, tanks of noble liquids kept cleaner than a hospital, sensors tuned to notice a single flash where no flash should be. So far, the greatest sensitivity has heard only the room tone of the universe. Another possibility is even quieter: the axion, born not from desires to explain galaxies, but from a neat repair in the mathematics of the strong force. If axions exist, they would be feather-light and numerous, rippling more like a field than like a rain of bullets. The way to listen for them is strange and elegant. Tune a copper cavity like a musical instrument inside a magnetic field. Sweep through frequencies and watch for a whisper that appears where there should be none. It is a physics radio, searching the static for a note composed by the dark itself. There are other candidates: sterile neutrinos, cousins of the ghost-like particles that cross the Earth by the trillions each second, would barely interact with the matter we know. Primordial black holes, collapsed pockets from the very early universe, have been proposed, then hemmed in by micro-lensing surveys and the way they would disturb starlight and gas. Each idea is tightened by data, as if the dark were being outlined by threads that pull inward from all sides. Not every astronomer is content to add a new ingredient to the cosmic pantry. An alternative path asks whether gravity itself needs a correction in the very weak fields that rule galaxy outskirts. Modified gravity models can fit many rotation curves with graceful economy. They are less at ease with clusters, the microwave afterglow, and the lensing in colliding clusters, where mass and light part company. The debate is not a quarrel, so much as a measurement. Two pictures of the same sky vying where the data are most precise. Each success counts, each failure leaves a chalk mark to return to. On smaller scales, the dark's behaviour meets granular puzzles. Simulations that start with cold, collisionless dark matter often grow halos with dense pointed centres. Some dwarf galaxies appear to own flatter, softer cores. There are too many simulated subhalos compared to satellites once counted around the Milky Way, though new surveys continue to find dim companions that narrow the gap. Feedback from ordinary matter, bursts of star formation, winds from supernovae, can puff out central densities and erase some substructure, bringing models and galaxies closer. The picture improves, then blurs again, like a shoreline seen through heat. The most persuasive evidence for the dark remains geometric and dynamical, how things move and how light bends. Weak lensing surveys smear the shapes of millions of background galaxies by a hair's breadth, then stack those tiny distortions into maps of mass that do not care whether that mass shines. Redshift surveys lay out the three-dimensional web of galaxies and show baryon acoustic oscillations, frozen ripples in the distribution that tie present structure to the early universe score. Change the dark matter and the rhythm of those ripples goes wrong. Keep it and the beat continues. If this sounds settled, it is not. The existence of a dominant unseen mass is the sturdy part. Its identity is the open question. We live in the middle of the experiment. In laboratories buried beneath mountains, photomultipliers hold their breath for a single characteristic spark. In radio-quiet valleys, microwave cavities slide their tuning rods by fractions of a hair, combing the dial. In space, telescopes watch galaxy clusters collide and record the parting of gas and mass with finer and finer hands. Each method is a different sense, the ear, the eye, the fingertip, learning to recognize a visitor we have only inferred. There is a gentleness to this search that suits the night. The dark we are after does not push back like a storm. It shapes quietly, everywhere at once. Without it, the young universe would have struggled to grow galaxies in time. With it, filaments formed like frost on a window, and light had a frame to climb. If the identity turns out to be a new particle, the standard model of physics will open a small, precise door and make room. If gravity needs a new stanza, the poem will learn a different meter in its softest lines. Either way, what seems impossible now will acquire steps, and the steps will feel obvious in hindsight. Imagine for a moment an empty room far under rock, chilled air, still wires, a pool of liquid argon waiting in its steel. Overhead, millions of tons of stone mute the noise of cosmic rays. Inside, the detector listens. Most nights bring nothing but the counting of its own atoms. Yet the whole instrument is arranged around the belief that the missing weight of the universe passes through that room as casually as moonlight passes through glass. Somewhere, someday, one of those passers-by may leave a fingerprint, a small recoil, a quiet photon, and the story we tell about galaxies will tilt from inference to acquaintance. Until then, we live under an invisible architecture that has never failed us. The Milky Way's arms hold together. The sun keeps time on a path carved by mass we do not see. The night, mapped by light, is steadied by what light cannot show. If there is comfort in that, it is not the comfort of completion, but of being held by a structure larger than our present words. The grass moves, the wind is real. Astronomers once set out with a simple expectation. The farther a standard candle is, the dimmer it should appear, and the pattern of that dimming should tell a clean story about how the universe slows with time. They chose a kind of exploding star as the candle, bright and reliable enough to mark vast distances. Night after night, they measured. They wrote down magnitudes and redshifts. They compared near to far. The surprise was quiet and unmistakable. The most distant candles were dimmer than a slowing cosmos could allow. They looked as if the fabric between us had stretched more than it should have by the time their light arrived. A cosmos that slows is easy to picture. Gravity gathers, motion ebbs. A cosmos that speeds up requires a new ingredient, not a gust of wind, but a property of the fabric itself. A soft pressure that lives in every patch of space and leans on the equations in a particular direction. We call that ingredient dark energy. The name is plain on purpose. It does not claim to know the cause, it names the effect, the way a tide names the pull without showing the moon. The gentlest picture is also the strangest. If the vacuum carries energy, then every cubic meter of empty space has the same small push inside it. As space grows, there is simply more of it to do the pushing. The result is acceleration without a motor. Distances lengthen at a pace that slowly increases. In the language of cosmology, this looks like an equation of state near -1, a pressure that is negative and precisely tuned. In plain terms, it is emptiness behaving like a hand on the universe's shoulders, nudging, never tired. Other lines of evidence met the candles halfway. Patterns in the oldest light, the faint microwave glow from when the universe first became transparent, speak of a geometry that is nearly flat. To keep that flatness while matching everything else we see, a large, smooth component must be present, one that does not clump like matter. Maps of galaxies show ripples in their large-scale arrangement, fossil imprints of ancient sound waves. The spacing of those ripples, compared across time, tells the same story. The expansion has been speeding up in the recent third of cosmic history. Each method has its own uncertainties. Together, they make a careful chord. What dark energy is remains open in a way that invites both rest and curiosity. The simplest possibility is a cosmological constant, a number that Einstein once added to hold a steady universe and later abandoned, not because the number was impossible, but because the steady universe was not. Brought back, it plays a different role, not to stop the expansion, but to make sure it does not drift toward a halt. If the constant is the answer, a deep puzzle hides beneath its calm surface. Quantum fields hint at an enormous vacuum energy that should bend space violently. The number we infer from the sky is small and precise. The mismatch is not an error bar, it is a canyon. Why those two counts differ is a riddle with no satisfying sketch on the napkin yet. There are livelier ideas that keep the acceleration, but trade the constant for motion. A field that creeps downhill in a very shallow potential could mimic a nearly constant pressure while shifting slightly with time. Such quintessence would not be uniform in its future behaviour. Its pressure would be close to, but perhaps not exactly, the value for a true cosmological constant. It would leave fingerprints in the way structures grow and the way the expansion measures change. Observers look for those fingerprints with patience, comparing the size of ripples in the galaxy distribution at one era to those in another, measuring how light from the oldest glow is polarized by subtle patterns in space, watching for small drifts in a parameter that has so far refused to wander. A different path moves the puzzle into the law of gravity itself. Perhaps on very large, very gentle scales, gravity follows a slightly altered rule, one that allows acceleration without adding a new substance to the inventory. These ideas knit the math with care, making sure that orbits in the solar system remain as they are, and that the early universe still grows the scaffolding of today's galaxies. Then they step out to the largest scales and ask the sky to choose between close cousins. So far, the sky is polite. It leans toward dark energy that looks constant, but it has not quite closed the door. There are two questions that sit like smooth stones at the bottom of this subject. The first is the one of magnitude. If the vacuum has energy, why is it so small? The second is the timing. Why does this small push matter now, in the same long season when galaxies are bright and stars still form? Earlier, matter ruled and slowed the expansion. Later, if dark energy stays constant, acceleration will dominate so completely that distant structures will slide from view. We live in the narrow middle where both contributions are comparable. It could be coincidence, it could be selection, it could be a sign that our simple picture wants one more thread. Acceleration changes the geometry of what is reachable as well as what is visible. In a universe that speeds up, there is an event horizon, not a wall but a limit to influence. Beyond a certain distance, a signal sent today will never arrive, no matter how long you wait. Light that now reaches us from far galaxies will continue to arrive for a while, reddening into longer and longer waves, then thinning below any instrument's patience. The night of the deep future will not be empty, it will be local. Bound groups will remain, the rest will fade into a background that is more silence than song. This is not a crisis, it is a consequence. Horizons are part of the grammar of expansion. Close by, nothing tears. The local group sits in its own quiet eddy, held by gravity and indifferent to the outward flow beyond. Dark energy does not pry apart what gravity has tied, it alters the drift of what lies between the knots. That is why Andromeda still comes, why clusters still hold their members, why the structures born early continue their private conversations while the larger river runs faster. How do we learn more without waking the night? We count and map with instruments that are themselves patient. Wide surveys trace the slight shearing of galaxy shapes by intervening mass. That weak lensing tells us how structure grows under the influence of matter and of the gentle push that opposes it. Supernova programs extend their reach with new calibrations and better control of dust and selection, measuring the curve of distance with finer chalk. Baryon acoustic oscillations, the ripples from the young universe, are followed across time, their spacing a ruler we can carry from one epoch to the next. Every method checks the others. Every result adds a thread to a net we are still weaving. It helps to keep one image in mind, simple and precise. Imagine space marked with a faint grid, squares that expand as time passes. If dark energy is a constant property of the vacuum, then each square carries the same small push as every other square. As the grid grows, there are more squares. The total push grows with them. Nothing is being poured into the system. No hidden engine whirs. The rule is built into the fabric. The effect is a slow tilt that accumulates. Stand with that for a moment. The most distant candles were too dim. The inference changed our map. The map led to new measures that agreed. The name we gave the cause described only what it did. What it is remains open in a way that feels both exact and generous. There is room here for new physics. There is also room for the possibility that the quietest answer, a constant, everywhere the same, will endure. Either way, the mystery is not a thorn, it is a horizon. The night is not less calm for having found it, it is larger and more awake and no less kind. Begin with a horizon that refuses to stay put. Walk toward it in your mind. It retreats with perfect grace, as if distance were a living thing that prefers to keep company without being caught. That is the feeling behind the question of size. Not a wall at the edge of everything, but a view that keeps widening as time gives light longer to arrive. What we can see is set by time, not by fences. Since the first hot light began its long journey, only so much of the cosmos has had time to speak to us. That reach is the observable universe, a sphere centered not on Earth the place, but on wherever you are listening. Every observer, anywhere, sits at the center of their own sphere, the way every swimmer sits at the center of their own ripples. Beyond the observable is not a void, it is simply more, waiting for enough time to pass. The oldest light we can actually see is a shell of faint microwave glow, the afterimage of a young, opaque universe turning transparent. We look in any direction and meet the same mottled sphere like a lantern in fog. But that shell is not the edge of existence. It is the limit of sight in photons. If the cosmos extends far beyond that shell, and every line of evidence says it does, its distant parts are hidden for now by the simple arithmetic of travel time. Shape is the second part of the riddle. On very large scales, the universe appears almost perfectly flat. In quiet terms, this means triangles add up the way they do on a tabletop rather than on a sphere or a saddle, and small ripples in the oldest light fall into a pattern best explained by a geometry without strong curvature. Flatness does not prove infinity. It says that if space is curved at all, the bend is so gentle that the portion we can survey is a tiny patch on a much larger shape. The total could be endless. It could be vast yet finite, like the surface of a sphere or a room with sides that wrap back on themselves without seams. We test for clever wraparounds by searching the ancient glow for matching circles, pairs of patterns that would repeat if the cosmos was small enough and multiply connected. So far, the sky keeps its patterns single. Two kinds of edge can confuse a patient mind, so it helps to choose words carefully. The particle horizon is the farthest distance from which any signal could have reached us since the beginning, that one moves outward as time passes, because there is more time for light to cross more space. The Hubble sphere is closer in. the distance where cosmic expansion makes galaxies recede at the speed of light. That is not a hard boundary, because light emitted inside it now can still cross it later as the expansion rate changes. The event horizon is different again, a limit to what can ever affect us if the expansion continues to accelerate. Beyond it, events happening today are already out of reach forever, no matter how long we wait. None of these are rims. Each is a horizon with its own rule. It can feel strange that space expands without expanding into something. The image that helps is simple. Mark a grid on a rubber sheet. Let the squares stretch. Nothing sits above or outside the sheet. The stretching is a change of distance within the sheet itself. In 3 dimensions, substitute space for rubber and the sheet for everything. There is no preferred center to the stretching. From each galaxy, all the others recede on average. From each, the view looks similar at sufficient scale. We are not at the middle. We are at a place, and every place has the same right to say so. Measurements knit these ideas into a single cloth. The tiny peaks and valleys in the ancient glow act like a ruler. Their spacing tells us about geometry. Ripples frozen into the distribution of galaxies, the faint memory of sound waves when the universe was young, give us a second ruler at later times. The way standard candles dim with distance offers a curve to compare against both. When all 3 agree, we learn about size without ever touching an edge. The agreement is not a shout. It is the soft consonants of instruments tuned to the same note. What, then, lies beyond what we can see? The most modest answer is more of the same, statistically speaking. Filaments of galaxies, wide voids, knots where clusters gather, repeating with patience. If the total is finite, the pattern returns without seams. If the total is infinite, the pattern continues without end. In either case, the part we inhabit is not special. The map grows pale at the borders of observation, not because the land ends, but because our light does. There are wilder possibilities, kept in the literature like sealed letters. Space might close on itself, in a shape more intricate than a sphere, giving a traveller who went far enough a chance to return without ever turning around. Or the cosmos might be stitched from domains that share rules, but not details, separated by distances that can never be crossed. These speculations are not for losing sleep. They are reminders that knowledge has room to grow without turning urgent. The presence of dark energy adds a gentle twist to the tale. If acceleration continues, the event horizon defines a permanent limit to influence. The observable sphere will still grow, we will still receive light from more distant pasts, but fewer new places will ever come into causal contact. Bound groups remain, the rest slide beyond lasting conversation. In such a future, the question how large will feel local by necessity. Yet even then, the inference we make now will hold. The part we can see is a small neighbourhood in a far larger city. Hold one image as the chapter's compass. You are at sea at night, the water is calm, the sky is unbroken. The circle of horizon around you is not the rim of the ocean, it is the edge of your view. As the night wears on and your eyes adjust, as the moon lifts and sets, as clouds loosen, the circle widens and narrows, always honest about what it can enclose. The sea does not change because your view does. The universe is like that, with the added kindness that time itself improves the sight. So the answer arrives without drama. The universe we can observe is large beyond daily scale. The universe that exists is larger still. Whether vast or endless, flat or gently wrapped, it keeps its edges as horizons that move with time and with the quiet rules of expansion. No wall waits in the dark. There is only a view that grows and a map that refines, and the steady feeling that our small circle sits inside a much wider calm. Imagine a map whose ink fades at the outskirts, not because the land ends, but because the light that draws it has only travelled so far. The universe feels like that, a chart sketched by time itself, the lines darkest where signals have had the longest to arrive, paling where they have not yet come. When we ask for an edge, we borrow a word from rooms and walls and carry it into a place where it does not quite belong. Space has no cliff face, no rim where stars spill out. What we meet instead are horizons, boundaries set not by fences, but by time and by the way distance behaves when space itself can stretch. One horizon is simple to picture. Since the hot beginning, light has been moving toward us at a constant, unhurried speed. It has had a finite number of years to work with. The farthest matter that could possibly have sent a photon here by now lies on what astronomers call the particle horizon. Look out in any direction, and it is there, a distance traced by the oldest signals that could have crossed the widening gulf in the time available. Wait longer, and that horizon recedes. The map takes more ink. The room grows wider without anyone moving a wall. Another horizon looks like a lantern in mist. Long before stars, before galaxies, the universe was a hot, bright fog of charged particles and light tangled together. About 380,000 years after the beginning, it cooled enough for electrons to settle into atoms, and space turned transparent. The light released in that transition still flows through everything, cooled into microwaves by the expansion, a faint, mottled shell that surrounds us from every direction. It is the oldest scene we can actually see with photons, the last scattering surface, not the edge of existence, but the edge of sight in light. The tiny temperature ripples on that shell are fossils of sound in a young cosmos. They mark places slightly denser and thinner, seeds from which the later web of galaxies grew. Edges multiply if we aren't careful with words. There is the Hubble sphere, a distance where the average recession speed, due to expansion, equals the speed of light. It suggests a barrier, and is not one. Light emitted inside it can travel inward, as the universe changes and still reach us. Light emitted outside it can someday cross into it. The event horizon is different, a limit set by acceleration. If the expansion continues to speed up, there will be regions so far that a signal sent from there today can never arrive here, no matter how long we wait. Not a wall in space, but a boundary in causality, a line beyond which conversation is permanently impossible. The mind wants to know what lies past these horizons, and the sky answers softly, more of the same, in the statistical sense. On the largest scales we can measure, the universe looks the same in every direction and from any location. That principle, tested by the evenness of the ancient glow and the spread of galaxies, suggests that filaments and voids continue beyond our current reach, like a pattern on fabric that keeps repeating outside the frame. The geometry we read from the oldest light is nearly flat. In calm terms, triangles add up, as they do on a table, not as on a sphere or a saddle. Flatness does not prove infinity. It does say that if space curves at all, it does so gently that the patch we can survey is a small piece of a much larger shape. Perhaps endless, perhaps finite, yet unbounded, like a room whose walls wrap back on themselves so neatly you never find a seam. There are older messengers than light, barely heard. A bath of relic neutrinos should pervade space, released when the universe was about a second old. They are almost untouchable, passing through matter as if it were lace, and their direct detection remains a quiet ambition. Gravitational waves, ripples in space-time itself, could carry news from even earlier, perhaps from inflation, the brief, enormous stretching that may have preceded the hot beginning we can test. If such waves exist in sufficient strength, they would leave a distinct curl in the polarization of the ancient light. Instruments listen for that curl, subtracting foregrounds with monastic patience, aware that a positive signal would open a window a fraction of a second wide, and older than any photon can show. Misconceptions make friendly ghosts here. Space does not expand into anything. Distances grow within space itself, the way squares inked on a rubber sheet widen when the sheet is stretched. There is no special centre. From any galaxy's point of view, all the others recede on average. The pattern looks the same in the round. When we say observable universe, we mean a sphere centred on the observer, defined by time since the beginning, Everywhere in the cosmos owns such a sphere, and none is privileged. How large is the part we can defend with numbers? Rulers abound. The ripples in the ancient glow set a calibration that carries into the later arrangement of galaxies. Within that arrangement, a frozen memory of sound, baryon acoustic oscillations, creates a faint, preferred spacing. We measure that spacing nearby and far away and compare. Standard candles, like certain supernovae, add their own curve, tying dimness to distance in a way that checks the others. Agreement across methods suggests a cosmos vast beyond our survey, and flat within our current sensitivity. The details shift as instruments refine, but the portrait holds horizons that are temporal, a size that is not bounded by a rim. The presence of dark energy folds a quiet fate into the picture. If acceleration endures, the event horizon becomes a permanent fact. Our observable sphere will still grow with time. New light from old, more distant pasts will still arrive. Redder and slower, but fewer fresh regions will ever come into causal contact. Bound groupings like our local group will keep their conversations. The rest will fade into a background that slides below any practical whisper. Even that is not an ending. It is a recalibration of what near and far will mean to any future watcher. There are stranger possibilities kept carefully on the shelf. Space might have a topology more intricate than a simple stretch, wraps and identifications that would repeat patterns in the ancient glow like matched circles at opposite sides of the sky. Searches for such echoes have found none compelling so far, or there may be vast domains beyond our horizon where initial conditions differ in ways that leave the laws intact but the details altered. These are speculations offered without urgency. The part we can test is generous enough. The edge that matters most is not a place, but a practice. We extend our sight with new messengers. Light at longer and shorter wavelengths, whispers in polarization, the faint shearing of distant galaxy shapes by intervening mass. We listen for neutrinos made gentle by age, for gravitational waves stretched thin by the very expansion they describe. We go looking not for a wall to touch, but for more ways to draw the map, where the ink has been pale. Hold one image and let it be simple. You are at sea at night. The circle of horizon around you is exact and shifting. It moves with weather, with moonlight, with the way your eyes adjust to dark. The ocean does not answer to that circle. It is larger, indifferent, and continuous. The universe is like that, with one more kindness. Time itself widens the view. Every moment adds the possibility of farther light, new marks on the chart, a broader calm in which to set the question down and let it be large. The hardest part is not that space can make letters, it's how those letters learn to speak. Bases, sugars and phosphates appear in the dark with patient regularity, yet the sentence of life remains a gap, across which we can see but not quite cross. In cold clouds, dust grains wear thin ice, water, methanol, carbon monoxide, ammonia. Ultraviolet light and cosmic rays tap gently at those coats, rearranging bonds until small precursors gather. Hydrogen cyanide, formaldehyde, formamide. In the lab, mixtures like these yield nuclear-based scaffolds, and simple sugars when chilled, lit and warmed. So the ingredients exist. The question is where and how often did nature collect enough of them in one place to matter? A nursery of stars is vast, chemistry there is sparse, a young planet must inherit that faint handwriting in bulk, or in many small deliveries. Which did it prefer? Carbonaceous meteorites and comet dust bring news from that dark. We have found glycine, we have found uracil, we have found reactive phosphorus, locked in strange minerals that wake in water. The inventory is rich, yet it is not a blueprint. Did those stones deliver the exact letters needed, or only a tilt in the pantry that early Earth could amplify? If circularly polarized starlight really nudged certain mirror forms to dominate in clouds? Did that bias survive the fire of entry and the wash of oceans, or did handedness start over on the ground? The signs point in both directions, and the balance is still unweighed. From letters to nucleotides, here the riddle sharpens. A nucleotide is 3 parts married precisely: a base to a sugar, a phosphate to the sugar's backbone. How did ribose, the shy sugar of RNA, endure long enough to be chosen? In beakers, ribose appears in the foremost network and vanishes again unless borate stabilizes it, or cold concentrates it in briny ice. Were borate-rich basins common on early Earth? Did ice act as a gentle freezer that both protects and crowds? We do not know which landscape carried ribose across its fragile hours. Even with ribose present, the bond to the base must be the correct one. Random coupling throws off a tangle of wrong attachments. Life uses a single, quiet geometry. Could sunlight act as a sieve, breaking the unstable linkages faster than the stable, leaving the right isomer to accumulate day after day? Could mineral terraces, montmorillonite clays, metal sulfides, guide the pieces into better fits? Experiments hint yes to both, but they do not yet show a path that runs by itself for long. How did the environment select with such stubborn patience outside any flask? Phosphate is abundant in rock, yet reluctant in water. It must be coaxed into energy-rich forms. Where did the activation come from? Perhaps volcanic drying forged condensed phosphates on hot ground. Perhaps urea and simple amidophosphates primed the bond. Perhaps meteoritic schreibosite dissolved as phosphite and struck first. Each route works in pieces. None is proven at planetary scale. Which reservoirs were large enough? Which cycles were frequent enough to make activation routine rather than rare? Chains are where the breath catches. Short strands can form during drying on warm stones, or within salt-rich ice where unfrozen channels crowd monomers close. Activated nucleotides will link on templates and copy short runs. Yet non-enzymatic copying stumbles on mixed sequences and high error rates. How did early polymers cross the threshold from some copying to copying that improves itself? Maybe helper groups such as imidazoles, made in the same prebiotic gardens, armed the monomers. Maybe magnesium ion, softened by citrate or malate, steadied both strands and membranes together. We can make parts of this harmony sing. The full chorus remains off stage. Was RNA even first? PNA and TNA, simpler backbones that still obey the code of pairing, form more easily under certain conditions, and could have learned to copy before passing the role onward. If so, what forced the handover to RNA? Was it ribose's better fit for catalysis, its flexible ring that lets strands fold into small enzymes? Or did chance fix one path and chemistry polished it later? The fossil record of molecules is thinner than stone. We infer from plausibility rather than bones. Compartmentalization arrives as both helper and hazard. Fatty acid vesicles grow, divide, and trap strands. But the very ions that speed template copying can burst those simple membranes. How did early systems keep both talents, copying and containment, in the same puddle? Chelators that tame magnesium point to a truce. Rock pores that separate zones by size hint at a scaffold. Ice that shelters channels suggests a winter classroom where fragile partnerships survive. Which classroom mattered most? Did they alternate like seasons rather than compete? Where did the cycles run? Warm ponds that breathe in wet and dry, volcanic beaches laced with glass, hydrothermal pores where heat flows from stone to sea, briny ice under pale suns. Each solves a different constraint, and each breaks another. Wet-dry rhythms drive condensation, but sunlight can unwrite what it composes. Vent gradients feed energy, but dilute the very reagents they power. Ice protects bonds, while slowing reactions to a crawl. Did life's rehearsal migrate between terrains, borrowing the strength of each in turn? The map is not wrong, it is incomplete. Space remains more than a backdrop. Interstellar ice chemistry supplies bases and sugar precursors. Polarized light may plant a minute preference for one hand. Meteoritic minerals contribute reactive phosphorus. Comets deliver reservoirs of organics to coasts that count time in tides. Yet the scale of that help is not fixed. Was bombardment a steady drizzle or a few decisive storms? Did ingredients fall where cycles were ready to work, or did they gather first in basins before being stirred into shallows? We read timing from craters and geochemistry. The script still has gaps. Selection likely began before life. The canonical nucleobases we use are unusually photostable. Close cousins bleach quicker under ultraviolet light. A sunlit pond is a quiet editor. A million small deletions can sharpen what remains. But photostability is not function. How did strands that survive the day also learn to fold and help their own growth at night? Ribozymes, small RNAs that catalyze reactions, arise in selection experiments from random pools, given time and care. Could a shore with cycles play the same game without a human hand? No one has shown it end to end. What would count as a satisfying bridge across this gap? A sustained cycle, run with natural minerals and sunlight, that takes simple, plausible monomers through activation, linkage, template copying, and occasional ligation, while a coexisting membrane grows and divides, and the whole system biases towards sequences that copy better over many rounds. Pieces of this exist. The whole still waits. The question is not whether chemistry can, but whether the planet did. And where? Hold a single steady image while the questions keep their place. A shallow basin on a young coastline, volcanic glass underfoot, a film of water shrinking under a thin sun. From above, dust from a passing comet falls for days, light as ash. In the film, activated nucleotides nudged by mineral steps find their neighbours. Night draws dew across the rock. Strands relax on templates and test pairings by moonlight. In the morning, the weakest bonds are gone. The better ones remain to grow. A vesicle at the margin fattens. A pore in the rock traps a cluster of strands, long enough for one to help another join. None of this proves inevitability. It shows how near the sentence may have been to writing itself, and where the line is still faint. The mystery is not missing, it is the spine. Which landscape set the pace? Which activation fed the bonds? Which backbone spoke first? How the error threshold was crossed? How the battery of energy was found and kept? Each question has partial answers that do not settle the night. That is the honest place to rest. A corridor lit by many small lamps, endings we can see from both sides, and the middle still dark enough to keep wonder awake without stealing sleep. Imagine a door that only opens outward, a fountain that never drinks, a shoreline where waves roll away from the sand and never return. Physics knows how to write such scenes on paper. Whether nature has ever staged one in the dark is the question that keeps this chapter awake. In the mathematics of general relativity, you can take a black hole solution and reverse the direction of time. What falls in becomes what must come out. The horizon that admits everything becomes a boundary from which nothing may enter. The result is a white hole. Matter and light emerge, but no signal can cross inward to touch the source. Drawn on a Kruskal diagram, the full eternal geometry shows 4 regions, including an exit partner to the familiar entrance. The picture is crisp. The problem begins when you ask how such a thing could form in a universe that grows by collapse rather than by unspooling. Black holes are easy to start. Let enough mass fall within a small enough sphere. Gravity overtakes pressure. A horizon forms. The rest is hidden. The time reverse asks for a horizon that always existed, prepared since the beginning, poised to eject a perfectly arranged outflow, while somehow remaining untouched by the messy, noisy universe around it. The slightest disturbance ruins the script. A single stray particle approaching a white hole arrives not after, but before, the emission in the time-reversed sense. The equations say that disturbance collapses the geometry back into a black hole. Instability sits at the door like a quiet guard. Thermodynamics offers its own reservations. The area of a black hole's horizon behaves like entropy. In classical gravity, it does not decrease. Reverse the movie, and you watch entropy flow down the gradient, order produced from disorder without a compensating cost. You can fix the accounting with radiation and careful conditions, but then you are writing an initial state so special that the cure looks like a restatement of the mystery. The arrow of time is not a law, it is a boundary condition. White holes ask for a boundary that feels far more precise than anything we have reason to expect in nature. Quantum ideas enter softly, promising a way to dodge a singular conclusion. In some loop quantum gravity models, the crushing core of a black hole does not become a point of infinite curvature. It reaches a maximum density and bounces. Inside, the proper time from bounce to emergence could be short. Outside, time dilates so severely that eons pass before the rebound is seen. The proposal even has a name you can hold gently: a Planck star. If such bounces occur, then every black hole would one day open as a white hole, not eternal, but brief, releasing information in a long-delayed exhale. The questions follow in a small, steady line. Or can a semi-classical horizon survive that long without dissolving completely into Hawking radiation? What spectrum would the final release carry? Would it be a sharp flash or a drawn whisper? Where do the instabilities go when quantization roughens the geometry? Do they soften or simply hide under new parameters? Observations have been invited to the conversation, and a few phenomena have been asked politely whether they might be white hole-like in disguise. Short gamma-ray bursts, fast radio bursts, or rare high-energy transients have been considered as candidates for a late-time eruption from small bounces. Each comes with its own established weather: neutron star mergers, magnetar flares, shock physics in plasma. The problem is not that a bounce cannot make a bright event, it is that the sky already has bright events with explanations that fit most of what we see. To move the needle, a white hole would need a signature that cannot be waved away, a spectrum or a timescale, or a polarization pattern that refuses the usual stories. No such refusal has held. Wormholes cast a longer, more cinematic shadow across this subject. In the ideal, a black hole mouth could be paired with a white hole mouth, connected by a throat that bypasses ordinary distance. The mathematics will let you draw the tunnel, the physics asks what keeps it from pinching shut. Traversable versions require matter with effectively negative energy density to hold the throat open. Quantum fields can supply negative energy in tiny local ways, as in the Casimir effect between close plates, but nothing we know provides the sustained macroscopic scaffolding a safe passage would need. There are ideas that braid entanglement with geometry, thoughts where a pair of entangled systems resembles a tiny bridge, a quiet ER equals EPR, written as a reminder rather than as a map. Even there, the bridge does not become a road. It remains an image of connection, not a tool for travel. Cosmology sometimes wanders over to peek through this door. Could the hot beginning we see as a Big Bang be the far end of a white hole? Could our entire universe be the interior of an outflow elsewhere? The proposal arrives with a certain symmetry. It leaves carrying baggage we do not see in the data. The early universe looks uniform and simple at large scales. It shows a pattern of ripples that fits inflation, a rapid stretching that irons out wrinkles and sets the seeds of structure. A white hole that births a universe must carry not only energy, but statistics. It must explain why the glow we see is so even, and why its small deviations have the shape of sound. The work is not impossible, it is unfinished. The mainstream view remains that bang and hole are different chapters, not two ends of the same pipe. If white holes exist in any sense, how could we recognize them? A true eternal white hole would be a source that repels all approach, an object you cannot accrete upon. That is a hard behavior to test, since everything else in the sky accepts a meal if offered. A bouncing remnant would be rarer, quieter for most of its life, then sudden at the end. The last stage of Hawking evaporation, if it ends in a quantum gravitational release, might look similar. Separating the two would take a fingerprint we do not yet know how to ask for. Even the absence of afterglow could mislead. Some magnetar flares fall dark quickly, some mergers blink and then hide in dust. The negative case teaches less than we wish. There are questions that remain crisp no matter where you place the bets. Does a consistent quantum theory of gravity forbid past horizons in realistic conditions? Does it permit short-lived ones as intermediates in a bounce? Does it require that information always exit, even if waiting longer than the age of galaxies to do so? Does cosmic censorship, the principle that nature hides singular misbehavior behind horizons, also hide the time reverses by making them impossible to set up without a bias we cannot justify? Can we write a space-time that is locally white hole-like in a small patch without inviting the instability that collapses it at once? The most honest statement we can make tonight is narrow and strong. White holes are allowed by the equations when written in their most symmetrical, eternal form. Universes that form structure the way ours does do not naturally make them. Quantum gravity might permit a late-time echo that resembles one. Observations have not demanded such echoes. They have not ruled them out with finality. The open space between these sentences is the unsolved portion. Hold one more image, not as proof, but as a way to keep the question gentle. On a chalkboard, a black hole diagram wears arrows that all point inward. Someone wipes them and redraws them outward. The shape remains the same. On paper, the reversal is clean and complete. In air, chalk dust hangs, disturbed by the eraser. The room refuses perfect reversal. Tiny currents write their own arrows as the dust falls. If a white hole belongs anywhere, it lives between those two stories, in the difference between diagrams that never smudge and a sky that always does. If one exists, it will not fix the night. It will broaden it. It will say that time's grammar admits more moods than our experience has heard. It will send a short message backward across a long patience and leave us to decide whether the message was always there, waiting for a name. Our galaxy is not at rest. Every star, every nebula, every quiet cloud of hydrogen in the Milky Way is riding a slow current, and the whole river is drifting toward a patch of sky we cannot see clearly. Light from the plane of our own galaxy lies in the way, a bright veil of dust and stars. Behind that veil, gravity has drawn a basin. We feel the pull. The shape of the basin is the question. Astronomers first sensed the motion as a tilt in the background light of the universe. The afterglow of the hot beginning is almost perfectly even, yet one side is slightly warmer, the other slightly cooler, a dipole that says, our local group is moving through that bath. The speed is calm by cosmic standards, and enormous by ours. It points towards Centaurus and Hydra, into a region now nicknamed the Great Attractor. The name is literal and provisional. It does not mark a single object. It names a destination we infer from the way nearby galaxies lean. Mapping an unseen valley begins with motions. Galaxies should recede from one another in proportion to distance carried by the expansion. Deviations from that smooth retreat, peculiar velocities, betray additional tugs. Measure both distance and redshift, and you can see where the flow lines bend. But distance is hard. We use standard candles and rulers, each with its temper. We collect thousands of measurements and smooth them into a field, the way a cartographer draws contours from scattered stakes. The contours point toward a low place. Now draw that low place behind the glare of the Milky Way, and you have the first sketch of an attractor. What sits there? Part of the answer is a cluster in the Norma constellation, Abel 3627, massive and close by, hiding in the zone of avoidance where dust and stars absorb optical light. Radio waves pass through more kindly, so does infrared. Surveys in those bands reveal galaxies masked to our eyes. X-ray maps show hot gas trapped in deep wells of gravity. Together, they outline a thickening of structure, a confluence of filaments near Centaurus and Hydra. The Great Attractor lives in that confluence. It is not a lighthouse, it is a shelf of land hidden by our own hillside. And yet the story does not end at Norma. Farther out lies the Shapley concentration, a heavier archipelago of clusters, hundreds of millions of light years away. Flow reconstructions that trace the paths of galaxies suggest our motion is not only toward the nearer basin, but also toward Shapley's larger country. How much each contributes is still being weighed. Some maps show flow lines bending first into the Great Attractor, then continuing on, like a river crossing a lake before dropping into a deeper valley downstream. Others give Shapley the lion's share from the start. The weights change as distance measures refine, the basin's outline shifts as new galaxies are added behind the veil. There is another actor, less tangible and just as real, emptiness. In the same way that hills pull, valleys push, underdense regions allow matter to slide away from them. Reconstructions of the nearby universe point to a broad void on the far side of our motion, a dipole repeller that complements the pull of Centaurus, Hydra and Shapley. The image that emerges is not a magnet but a landscape, a ridge of mass ahead, a hollow behind, and our local groups sliding downslope between them. How much of our drift belongs to the ridge, how much to the hollow, is part of the unsolved portion. The toolset is varied and patient. The Tully-Fisher relation ties the rotation speed of a spiral to its luminosity. The fundamental plane links the sizes, brightnesses, and stellar speeds in ellipticals. Supernovae add sharp signposts. Each method gives a distance with a personality. Systematic quirks, statistical scatter, that must be understood before many small truths can become one larger one. Once distances are in hand, redshift separates pure expansion from peculiar motion, and flow fields can be drawn. The latest atlases, cosmic flows, and its kin trace thousands of vectors and show tributaries curving towards Centaurus and beyond. The basin is there, its edges are still being followed with a fingertip. Meanwhile, the zone of avoidance shrinks as different eyes take their turn. Infrared surveys such as 2MASS revealed hidden swaths of nearby structure. 21-centimeter radio surveys map hydrogen-rich galaxies, even where dust is thickest. X-ray telescopes find the deep potential wells where gas is heated to millions of degrees. Each wavelength pulls another thread of the tapestry through the loom. The weave grows denser, the picture clarifies and complicates in equal measure. Beneath all of this lies the invisible majority. Dark matter carries most of the mass that shapes the flow, yet we see it only by what it does. Lensing, how gravity bends light from still more distant galaxies, lets us draw mass without light, but lensing is most powerful for far fields and massive clusters. In our backyard, peculiar motions are the cleaner tracer. The two approaches meet in the middle and check each other, but they do not yet lock into a single map without seams. The exact depth and breadth of the basin remain hazy, not because gravity is coy, but because measuring motion through a crowd is. Even the definition of attractor needs care. Gravity in general relativity is not a force that reaches out and grabs. It is the shape of space-time that tells matter how to move. In that sense, the Great Attractor is a curvature pattern written by mass along many filaments. The word persists because it captures the human experience of sliding downhill. We keep it and remember it is a metaphor. The open questions collect in a quiet list. How much of the local group's peculiar velocity is accounted for by the Centaurus Hydra region alone? How much requires Shapley's distant weight? How large is the contribution from the broad void behind us? What is the precise mass of the Norma cluster once all its unseen dark matter is counted? Are we sampling the sky deeply enough behind the densest parts of the Milky Way to avoid biases that shift the basin's apparent centre? Each question can be answered with better distance ladders, broader surveys, and cleaner models. None has a single decisive observation. The solution is cumulative, like filling a basin with rain. If you want to hold a clear image, let it be hydraulic. Picture the nearby universe as a watershed drawn in faint lines. Galaxies are leaves on a slow stream. The streams run along filaments toward confluences. Some water seeps away from broad, dry bowls. Currents join and thicken until they pour into a deep, distant valley. Our leaf rides one of those streams. The first bend in its path is near Centaurus and Hydra. The overall fall line points towards Shapley. Behind us, a high, dry plain slides the water forward. The map is still being shaded. The direction is steady. What will sharpen the contours? More distances, especially behind the veil. Better calibration of standard candles and rulers. Deeper radio and infrared surveys to find the hidden galaxies that anchor the flow. Wider, faster X-ray catalogues to weigh the hottest, deepest wells. In time, the basin will be drawn with lines that agree across methods, and the word Great Attractor will become less a riddle and more a chapter heading in the atlas. For now, the unsolved portion is not a hole in the floor. It is a mist over a valley we are already descending. We feel the slope in the background glow, see the currents in our neighbours, and watch the filaments arch toward the same quadrant of sky. The Milky Way's own light hides the view, and still the river is clear in the way it moves. On some night years from now, when the maps are thicker and the zone of avoidance is thinner, the basin will look less mysterious. The drift will be the same. The comfort is that both are true already. The motion is real, and the reason is one we are still learning to see. Here, at the edge of the lamplight, we have walked the unanswered paths. A moon lifted from fire, shorelines on Mars that wait for their water, two galaxies drawing a quiet bridge between them, an invisible scaffold that holds the night, a gentle pressure in emptiness, horizons that move as time moves. The questions remain, patient and exact. Let them be invitations rather than alarms. The bell of the early Earth keeps ringing softly. Dark matter moves the grass, though we cannot see the wind. The oldest glow hangs like a lantern in mist. Comets carry a small pantry. Through the dark, a hidden river of gravity draws our galaxy on. The unsolved portion is the room where wonder breathes. Now let the breath fall into an easy tide. In for 4, pause, out for 6. Shoulders loosen, jaw unclenches. The mind sets its books back on the shelf. Nothing more is needed tonight. The sky will keep its questions. Sleep comes on the next slow exhale. Good night, Voyager.